In the last learning sequence, we talked extensively about the force that a magnetic field applies to a moving charge. And we talked a little bit about how magnetic fields are also made by moving charge. We had a little bit of current in a wire, that's a moving charge. We had a field going around the wire. If we had current in a loop, you made a field inside. We talked about natural magnets. They're actually little atomic currents flying, going around the atoms. But now what we're going to do in this learning sequence is talk about making a magnetic field in more detail with math. Okay? So you do that with a law called Biot-Savart. And they were both French, so the T's are silent. If I had to define the Biot-Savart law, I would say that it is the B field due to a current. Also, I'm going to just say current all the time. And that's just going to mean a wire carrying a current. Okay, so the wire is implied. Really, we're just speaking generally about really any current. Okay, but I'll draw them like they're wires. So let's imagine then we have some wire here. Doesn't have to be straight. Right now we're doing just the general Biot-Savart law for any current. Like that. There's a wire. It's got a current I flowing into it. Okay? And you want to know what's the magnetic field somewhere like here at point P. What magnetic field do these moving charges create? Okay? You're not asking much. That's all you want to know. So what is B at P? And you'd think we'd have some simple formula like Coulomb's law, but we don't, because there are no point currents, right? When we're doing electric fields, point charges can add up and give you this nice simple expression. But when we went to continuous charges, we had to do an integral. We had to have a differential. Well, with a magnetic field, we have to go straight to the differential because there's no point currents. Any current you have has to be some distributed current. It has to be flowing through a wire. You can't have one place where there's a current, because where did the charge come from and where did it go? So here, we have to go straight to a differential definition. So let's do that. So Biot-Savart would say then that you have to think about a little piece of the wire. You have to divide it up into little imaginary differential elements. So remember these things. Differential elements are just imaginary little chunks. And when we're thinking about these little things, then you can treat it like a point current. So one might be sitting here, and we give them a little vector differential ds. That just means the path. That's really the length in that case along the direction of the wire ds. And we want to know what differential magnetic field dB is created by this little differential element ds, and then we add them up for the whole wire. Okay. So the answer is dB at point P is mu naught over 4 pi, so it's a new constant, we'll define it in a minute, times the current, I, it's a big I, times ds crossed with r, hat. Oh my gosh, over r squared. So that looks horrible. It's got everything that you don't like in it. It's got a cross product inside of an integral with a vector differential and then just a unit vector just to make it extra horrible, okay? But let's go through and figure out what they are one at a time. So ds, we already talked about. We would call that the a differential element of the wire. Differential element of the wire. And its direction is, of course, along the wire. That's usually how you set up a differential element. R, let's look at R. R is the distance from the ds to the point P. And you'll see it written this way in books a lot with just an R. But if we really want to understand the whole setup, it's actually better to make it a vector and say it's the magnitude of that vector. It's the more formal way to say that it's the distance. That way we can define the vector here. Okay. If we do it that way, I can show you R. R is just the vector from ds to P. R is just the separation. So it's the vector ds to P. And now this makes r hat easier to identify and to draw. We know r hat would then just be the unit vector along that direction. So if I had to draw r hat, assuming unit was only that far, there's r hat right there. R hat, unit vector along r. And let's see, 4 is the fourth integer, and pi, you know what pi is, and mu naught, that's the one that is left. Mu naught is the permeability of free space. It's a lot like epsilon naught for the electric field, the permittivity of free space. How much electric field do you get for some charge? Permeability of free space helps you figure out how much magnetic field you get for some current. It's equal to 4 pi times 10 to the 7th. It must be Tesla meters per amp. That's the constant you want to use. 4 pi times 10 to the 7th Tesla meters per amp. So now what we're going to do is keep going and think about how to do this integral.